Today we'll be beginning with chapter 6 of the syllabus, which is titled Chemical Energetics. And what we'll basically be talking about in this chapter is, first of all, fuels, and focusing on fossil fuel and crude oil. And then we'll be talking about exothermic and endothermic reactions, what those are, and how to represent them diagrammatically. Now, the part on fuels is there's nothing technical over here. I could ask you just to read through the book. I'm going to summarize it and move through it quickly, right? And the details you can definitely get from the text. And what I'll focus on is the second part, which is the exothermic and endothermic reaction. So when they talk about fuels, right, what is a fuel? So it is any substance that can be used as a source. Excuse me. It's any substance that can be used as a source of energy. All right. And so fossil fuels are one type of fuel. Right. They are organic hydrocarbons, meaning that, right, organic molecules, and saying hydrocarbon is sort of a repetition, because when we say that something is an organic molecule, and you got chapters on organic chemistry near the end of the syllabus, what this basically means is that the molecules are primarily made up of consist of the elements carbon and hydrogen. Salam alaikum.
Walaikum assalam.
All well?
Yes.
Okay. We've just begun.
Okay.
So fossil fuels are the kind of fuels that are used today, right? And they are actually the remains of plants and animals. They're derived from the remains of plants and animals that died over 200 million years ago, right? And energy is released from these via combustion, right? Combustion is basically them reacting with oxygen, right? They're burning. So when something burns, it combusts. So, right, what do you get when a fossil fuel burns an oxygen. You have a fossil fuel, and there are many different types, and so that's why we're writing fossil fuel plus oxygen, oxygen will give you ideally carbon dioxide and water. I say ideally because that's only if you have plenty of oxygen for that combustion to occur. So an example of this is methane, which is a gas, plus oxygen, obviously giving you carbon dioxide as we talked about, and water. What does it look like in terms of its formula? Methane is CH4, oxygen O2, carbon giving you CO2, and water giving you H2O. Is it balanced?
Mm, yeah.
Are you sure?
No, it's not balanced.
Then what would you do?
The carbon is not balanced.
The carbon's not balanced. Carbon's balanced. You've got one carbon here, you've got one carbon here.
Oh, yeah, the hydrogen. Sorry, the hydrogen.
Right, so you've got 4 hydrogens on the reactant side, you've got 2 hydrogens on the product side.
We can add 2 on the reactant side.
On the reactant side, 2
Product side.
Sorry, on the product side.
with the water.
Yeah.
And so now we've got 4 hydrogens, so hydrogen's happy. But now we've got 4 oxygens, and over here we only have 2 oxygens.
So we can add 2 on the product side or reactant side.
Yes, and now it's balanced. Now, right, as you've obviously noticed, we did balancing equations way back when, right? But whenever an equation pops up, I ask you to balance it. So that's something we're practicing on the go. So, right, this is what you would expect to get. And right, so natural gas is primarily methane. It's a mix of hydrocarbons, right? Uh, if you've heard of natural gas, right? If you heard of CNG, compressed natural gas, and so that's mainly methane, but it does have some other stuff mixed into it, right? Like ethane and propane, and then some sulfur. So that's information given in the text. Now, right, what would be the perfect fuel, right? The ideal fuel that's, just exactly like we would want it to be. And it's obviously hypothetical because there's no such thing as a perfect fuel or anything perfect. So the first thing it needs to be, it needs to cost less, right? So it shouldn't be expensive. It should be available in large quantities so we can use lots of it. All right, so the perfect fuel, the benchmark or the criteria for perfect is our, how we're going to end up using it. So we're going to use a lot of it, so we want a lot of it. It should be safe to store and transport. Right? It should easily burn, causing no pollution. And release no greenhouse gases. So that's a point given. So no pollution because greenhouse gases are considered as pollutants. and release large amounts of energy. Now, obviously, right, there's no such thing as a perfect fuel. And again, right, the primary fuel that we use in the world are fossil fuels. There are others, alternative fuels, and there are two types. So there are non-renewable, right, which are used up and you don't get more of them. And then they are renewable, right? Renewable doesn't mean that they're recycled, it just means you can get more of them, right? More is available easily. So for the renewable ones, right, I'm listing down some renewable options, and you've got nuclear fuel, tidal energy, hydroelectric energy, waves, biomass and biogas, geothermal, then you have hydrogen, solar, and wind. So hydrogen, we just talked about hydrogen fuel cells, the last class, solar, and wind. So, these are all renewable fuel sources, and many of these are used in different countries across the globe, right? Even nuclear fuel. But again, none of these are perfect.
Yeah.
Now, because we've been talking about, right, fossil fuels, and so the main fossil fuel that is used is oil. So we're going to talk briefly, and again, I'm not going into the details. The details are given in the text. So, right, you get oil from oil reserves as crude oil. And the reason it's called crude oil is it is a mix of many different hydrocarbons. So many different molecules, organic molecules, right? And so, right, and they differ in their boiling points. And their boiling points differ because of the different sizes of the molecule. So what happens is that crude oil is processed via a technique called fractional distillation. Right, and basically what happens is that they heat it to boiling, and so the vapor rises up a fractionating fractionating column, right, where it's cooler as it goes higher, and condenses the different fraction So the different fractions condense, right, uh, at the cooler region. So whichever part is cool enough for that vapor to, turn back into liquid. And this way, what you get is that you separate the mixture. Remember we talked about mixtures and compounds
Yeah.
way back when? And one of the things, the differences between mixtures and compounds is that you can separate the components of a mixture if their physical properties are sufficiently different, right? This is an example,
Yeah.
a practical example of that. So crude oil is a mixture, right? And so this process, the fractional distillation process, is used to separate. So they've got different boiling points, right? And different boiling points means different condensation points. So you heat it to the highest, right? Where almost all of the fractions will separate. And then when they start condensing, they condense at different temperatures. And so whichever fraction is at a certain temperature will separate, the rest will continue to rise, and then they'll keep condensing at lower and lower temperatures. Now keep in mind that, the fractions are still mixtures. So they're still not, separate substances, separate compounds. And so the technique is repeated, right, for each fraction. Obviously adjusting this time to the temperature requirements, because you want now something that condensed at around 100 degrees, right? But it's a mixture. So maybe it has something that would condense at 110, at 190. So it's got three different compounds mixed together. And so this time when you're doing fractional distillation, you will take care of having those three different temperature ranges for it to condense, so you can separate those out even further. Right, so that's what's happening. I'll show it to you in the text, and then we can move towards talking about the actual concepts of the important concepts of exothermic and endothermic reaction. Right, so this is all detail over here. Read it, right? And this is what a fractionating column looks like, fractional distillation. So you've got crude oil coming in, you're heating it up, right? And as you can see, the temperatures over here, it's 340 degrees centigrade, a bit higher, and it's 260, then 180, 110, 30, and then, right, really light. It doesn't condense, it's natural gas, right? So it stays as gas, it's not condensing, right? Maybe it has even a lower boiling point. And so these are different fractions. You need to know these, right? So there's bitumen, which doesn't, it's being collected down here, so it doesn't really boil. There's no vapor, so it just collects, right? And this is used for making roads. Then you've got lubricating fractions, which condenses almost immediately, right? And so for lubricants, waxes, and polishes, then you've got fuel oil, you've got diesel oil and gas oil, right? Then you've got kerosene for jet fuel at 180, at 110, you've got naphtha, right? It's a chemical feedstock. Then you've got 30 degrees, you've got gasoline or petrol, and that's why, right, petrol is volatile. So if you've got petrol in an open container, you can smell the fumes because it is, right, it is just, turning to, the vapors are escaping the liquid. And if you leave it out open for long enough, you will see that there's a decrease in volume of the liquid, the petrol, and pretty soon it's all gone. right? Because obviously if you have a condensation point, which means boiling point of 30 degrees centigrade, so if you leave it out in the open, it's not going to stick around, right? Very low boiling point uh, compared to the others. And then the lowest, obviously it doesn't even condense, you've got natural gas, refinery gas. Okay. One trend to notice with all of this is, let me just go back to the whiteboard. Is that as you move up the fractionating column from the bottom to the top, you have lower boiling points, as we just saw, and higher volatility. So again, right, it will give off fumes if it's left in the open. So higher volatility. Lower viscosity, so it's less thick and it flows easily. Viscosity is how thick a liquid is and how easily it flows. So if it's viscous, the viscosity is higher, right? Viscous, that means it's thick and it doesn't flow easily. So an example of that is honey, right? Honey is a viscous liquid. And then low viscosity, right? So water's there obviously, but even lower than water is oil, right? Petrol, it flows very easily and it's, right, not thick at all. So the viscosity decreases as you move up the fractionating column. And all of this is primarily because of a change at the molecular level, the decreasing length of the hydrocarbon chains. Now, what does that mean? We'll study about them organic chemistry. Right, but basically these hydrocarbons are in the form of chains, right? That's what they look like. You've got hydrogens all around. Right, and so this is a 5-carbon hydrocarbon. It has a name. I'm not going into that at the moment. And so the larger molecules, the larger hydrocarbon chains are lower down, so the bitumen and everything, and then up the petrol and the natural gas, those are shorter hydrocarbon chains. They're lighter, which makes them more volatile. They're smaller molecules, so they've got lower boiling points and they have low viscosity. They're not thick and they flow easily, all because they're smaller molecules. Any questions?
No, sir.
No.
Okay, now despite saying I'd not spend too much time on it, I just realized I already have spent too much time on it. So, moving on to exothermic and endothermic reaction.
Can I take a guess on exothermic?
Sure.
It takes out the heat.
You would say it gives off or releases.
Yeah. Okay. And endothermic that takes in heat.
Yes.
Okay.
Okay. So, an exothermic reaction, by definition, it transfers thermal energy to its surrounding.
Oh, the example can be like freezing.
No, freezing is not a reaction, that's a change of state.
Oh,
Right? There is loss of heat, obviously, right? But it's not a reaction. So freezing is exothermic perhaps, right? But not in terms of a reaction.
Okay.
So reactions that transfer thermal energy to its surroundings, leading to an increase in temperature. An increase in temperature of what? Of the surroundings. And then you got endothermic, which is the opposite. Right? It transfers thermal energy from the surroundings. So it takes in energy. Right? So the keyword over here is to. And so reactions that transfer thermal energy from, right? Keyword is from our surroundings, which means it's taking in, leading to a decrease in the temperature of the surroundings. Right. Now, an example, like most reactions, most chemical reactions are exothermic. Right? So generally they give out heat. And right, how exothermic they are, some, right, there's only a slight change. In others, a lot of heat is given out. So you can actually feel the beaker or the conical flask or whatever apparatus you're using actually getting hot. Right? They're that exothermic. So combustion is, right, when something burns in the supply of oxygen, and that is an example of an exothermic reaction. And because we've been talking about fuels and fossil fuels, right? And so the burning of fossil fuels is combustion. So, right, you've got a fuel, or more appropriately, fossil fuel. We've already done this, right? Plus oxygen gives you carbon dioxide plus water. And right, so again, methane plus oxygen gives you carbon dioxide and water. Balancing that out, we already done that. You've got a gas and another gas and a third gas and a liquid. So this is an exothermic reaction, right? And so the energy that we get from fossil fuels is initially as heat and light, right? And so how do we get that heat energy from fossil fuels? Via combustion, because it is exothermic. Right, so fossil fuels. Could you please mute your mic? Unless you have something to ask or
Yeah, okay.
not give energy but release energy as heat, right? Sometimes as light, and sometimes sound may be involved, right? but basically heat.
I did not understand the sound part.
Uh, have you ever, made barbecue?
Yeah. I mean, I've seen people do it. And
Have
yeah,
you
I've done it personally as well.
have you heard the crackling of the coal?
Oh, yeah, yeah, yeah.
Yeah.
Okay.
But again, right, that is, it comes much later. So it's basically heat,
Oh, okay.
right? And then followed by light,
Okay.
right? So a fire burning, that's providing you heat, it's providing you light as well,
Okay, got it.
right? So because sound comes in later, you can like, okay, fine, forget that. It's not relevant to our explanation anyway. All right, so this is what we're talking about, the exothermic reactions, giving off heat. Okay. And then obviously this heat is transferred to its surroundings, and so the temperature of surroundings increases. That makes sense. Now, this is in case of complete combustion, right? Complete combustion, which basically means, right, there is ample, right, oxygen. There's enough oxygen for this to happen. If there is insufficient oxygen, that would lead to incomplete combustion. And so the products would be slightly different, right? What you'll have is methane plus oxygen. So those are there, but knowing that it's not enough, you're going to get carbon monoxide and water, right? So where is the difference showing up? The difference is showing up in carbon monoxide. You've got less oxygen, and so you're getting carbon with only one oxygen, not two of them. So that's CH4 plus O2, giving you CO, not CO2, so because you've got less oxygen, and H2O. Gas, 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 and liquid. And this is definitely not balanced. It's a bit tricky. You want to try balancing it?
Yeah.
Go ahead.
Like we have to add two on the reactant side
For what? For
of
what?
hydrogen.
For
Hydrogen.
on the reactant side.
Sorry, on the product side.
Okay. So
And
so we have four hydrogens, and now we've got two oxygens, three oxygens on the product side, two oxygens on the reactant side. So the oxygen's not working out. The hydrogen's fine.
we can add three
Three for
hydrogen, and on the like reactant side we can add two for carbon.
on the reactant side, two for carbon. So that's giving me two carbons and eight hydrogens. So if I'm getting eight hydrogens,
Oh yeah, we have to add four.
so that would give me four over here.
Yeah.
I've got two carbons, so I'm going to add two over here. And so my carbons are balanced, my hydrogens are balanced, right? Now, how many oxygens do I have? I've got two oxygens here, and I've got two and four oxygens here. So that's six oxygens. So how do I balance oxygen?
Put three on the product reactant side for oxygen.
And we're balanced. So slightly tricky, right?
Yeah.
So this is incomplete combustion, right? And again, the incomplete part is showing up. You've got carbon dioxide and carbon monoxide. So two oxygens with the carbon with complete combustion because enough oxygen. When there's Oxygen's not enough, you only have one. And this is actually a far more polluting and toxic gas, right? So carbon monoxide is more dangerous than carbon dioxide, right? It's toxic. Carbon dioxide is not toxic. So this guy is very bad. Now, what you can do is you can show the changes taking place in a reaction by drawing a reaction pathway diagram. Alright, so a reaction pathway diagram shows changes taking place in a reaction in terms of energy. Right, and so generally for an exothermic versus an endothermic reaction, what will it look like, and what does it look like anyway? So let's draw this. All right, this is not a graph, so technically you don't need the axis. And you label them. So the y-axis is the progress of reaction.
अच्छा ब्रो, तुम कह रही थी ना तुम्हारे को अपनी अम्मी को बहुत मनाना पड़ेगा मॉल का. It's fine, we can do it at house as long as.
Sobia, your mic. All right, so that's the progress of reaction, and on the y-axis you've got energy. Doesn't look very good. Energy per kilojoules. Now, an exothermic reaction gives off energy, right? That means that the energy of the product is lower than the reactants. And so what you do is that you start from here, right? And these are reactants. And you show an energy decrease, that is the exothermic part, because energy is being given off. And you have the product. In the case of endothermic, the energy of products is higher than reactants. And so you start off low and you show an energy increase, and then you've got your product. So these are reactants and these are your products. Does this make sense?
Yeah.
Right? So in case of, for example, the combustion we just talked about, let's talk about complete combustion. So over here, what you'd have is CH4 plus O2. And over here, you would have CO2 plus H2O. Right? And these lines should join, by the way, right? So you actually draw the arrow in between. An example of an endothermic reaction right, is the reaction of nitrogen with oxygen. So you've got N2 plus O2, and that is giving you 2NO. And you need to write the states as well. So you've got all gases over here. These two are gases. This is a gas and this is a liquid, right? So that's what it looks like. Now, there is a bit left to talk about, right? They've given some examples of endothermic. We know endothermic. There is an example of an we know what exothermic is. They've given an example of an endothermic as well. Do you guys have like maybe 10-15 minutes to spare?
Okay.
Aram? Okay, I don't know. I just feel like I want to get through with this.
Yeah, okay.
So, along with this understanding, we need an understanding of what's happening when bonds are being broken and bonds are being made. So, right, when bonds are broken, right, energy is used. So it's taken in. And so breaking bonds is endothermic. They need an input of energy. When bonds are made, energy is released. And so energy, these are exothermic. Why is this important, right? How do I use this to tell whether a reaction overall is endothermic or exothermic? So what we have is that we have values of the energy of various bonds. And so I'll take you to the book for that. Let me put that on screen. And so what you can see over here, this table, right? The energy of the bond is called bond energy, obviously, right? It is measured as kilojoules per mole. What is a mole? We haven't talked about what that is. That's chapter 4, right? So it is a quantity. It is a quantity. Just keep that in mind,
Okay.
right? It is a quantity of a particular substance, an element, or a compound, or whatever it is. So this energy is the same whether the bond is being broken or it is made. What does that mean? If, for example, a carbon hydrogen single bond, right? So these are all covalent bonds. You should recognize by the way they're written, these are all covalent bonds, right? The double covalent bond between two oxygens and carbon and oxygen, the single covalent bond between hydrogen and oxygen, right? The single covalent bond between a carbon, oxygen, CH. And so if this bond is being broken, that means, for example, for a CH bond, 435 kilojoules of energy per mole is required as input to break this bond. And if this bond is being made, and so that's exothermic. And so for each for each bond, 435 kilojoules per mole of energy is released. Okay? Do you get that part?
Yeah. Okay.
Okay. So how do we, Haram, question?
No,
Okay. So how do we put that to use? Let me go back to the whiteboard.
it's like kind of confusing. So
What's confusing?
I don't know, like the bonds alone.
Have you reviewed the chapter on bonding from earlier?
Yeah,
Do you remember covalent bonds?
yeah,
Right? So
Like the atom share an electron, no? The
right,
covalent
and
bonding.
so right, you, you need to cause those that separation to end, right? To cause those atoms to separate from that bond, you need to supply energy, right? Because those electrons that are being shared are giving stability to those atoms that are bonded, right? So to separate them, you need to give energy and cause the electrons to move away, right? And on the flip, when they're coming together, they have a lot of energy and they're coming, the bond is forming, and so they're releasing that extra energy, so to speak, and coming to a stable position where they're happy. Okay, why is my whiteboard stalling? Okay, so right, the values of energy of various bonds are called bond energy, right? And these are the same for bond making or breaking. And so what do we do? So for example, we have CH4 plus O2 giving me CO2 plus H2O, right? This is what I have. And right, if I balance this out, then I have 2O2 and 2H2O, right? This is important as well. So when I'm going to calculate this, I want a balanced equation. Now, how many CH bonds are over here?
Uh,
4.
yeah,
Okay. How many bonds are here?
two,
2, because there are two molecules of oxygen. How many C double bond O are there?
Two.
two,
2. How many HO bonds are here?
two,
No.
four.
Hydrogen at 4 and oxygen at 2.
Yeah, but there are two molecules, so that makes it 4,
Oh,
right? And so this is the bond breaking side. The reactants are bond breaking side, and the products are the bond making side. Okay. So first we calculate the energy of these bonds. So how much is the energy of a CH bond? It's 435 kilojoules per mole times 4, and that gives me 1740 kilojoules per mole, right, for CH4. Then for oxygen, right, it's 497 times 2, which gives me 994 kilojoules per mole. And so, okay, that's not very. And so the total bond breaking energy is 2734 kilojoules, right? Then we come to the other side, the product side, which is bond making. And so we've got two of these carbon double bond O's, and so their energy is 803 and you've got two of them, and that gives you 1606 kilojoules. Then you've got the HO bonds, and those are individually 464. So this is the C double bond O, this is the HO, this is the CH, and this is the, okay. And so you've got 464 times 4, and that's giving you 1856. And so the total over here is 3462 kilojoules of energy. Now what you need to do is you need to take the difference between the reactants and the products, right? So the energy required to break the bonds and the energy given out when the bonds are made. So, right, energy difference equals to energy required to break bonds minus energy given off when bonds are made, right? And that would give me 2734 minus 3462, and that gives me a negative value of 728 kilojoules per mole of methane combusted, right? This negative sign is telling me that this is an exothermic reaction. So if
So when it's if it's a negative, then that's exothermic.
yes, if the difference, if the energy given off when bonds are made is higher than the energy that is required to break the bonds, right? If the energy on the, obviously the reactant side is lower than the energy on the, sorry, my bad, right? So if the energy required to break the bonds is lower than the energy required to, sorry, the energy given off when the bonds are made, and so the difference will be negative, and that tells me it's an endothermic reaction. Endothermic, sorry, exothermic, sorry,
Yeah.
exothermic reaction.
So the difference that when it's a difference and the answer comes out negative, that's exothermic, right?
Exactly, exactly.
Okay. And when you
If
and
it's
what's
if it's a positive sign,
yeah.
if energy difference is positive, then that would tell you it's an endothermic reaction.
Okay.
Now, right, the energy in bonds is called enthalpy, and it is symbolized by an italic H. And so, right, the change or the transfer of thermal energy during reactions is called the enthalpy change. And it is given with the symbol of delta. This triangle is called delta, which means change, and H for enthalpy, right? So delta H. I'm almost done. One last thing for a reaction that you need to know is the activation energy. The activation energy is the energy required to get the reaction going. So the minimum energy, and recall the kinetic particle model, the kinetic particle theory, the minimum energy that colliding particles must have to for in order to react. And so usually for a reaction to occur, it needs a slight input to start, even if it's an exothermic reaction. Does this make sense so far,
Yeah.
Haram?
Yeah.
Okay, finally, hopefully finally, right? Let's make a reaction pathway diagram for methane again.
Okay.
Something?
Nope.
Right, so you got progress of reaction, and you've got the energy per kilojoule, and you're starting with methane and oxygen up here. So that's CH4 plus O2. Now what you're going to show, it's going to look something like this. Now what is this? You've got your products, which are CO2 and O2. What's happening over here, right? Two things basically that are new. What is this? That is the energy difference, right, between the reactants and the products. That is the delta H. That is the enthalpy change, right? And because this is exothermic, as we know and we've calculated, you're going to put a minus sign over here. So it's negative enthalpy change. Energy is given off. Okay. And in fact, to be accurate, and this is important as far as your examinations are concerned, you want this arrow to be touching these dotted lines. Okay. Then what's this bump over here? That is the activation energy, right? And that is given as EA, and that A is actually a subscript, so small a over here, right? So activation energy, sorry. So this is what the energy diagram of an exothermic reaction would look like. And for an endothermic reaction, right? So again, you got progress of reaction, you've got energy per kilojoules, and you're starting from here. And again, so for example, you got nitrogen and oxygen. And so it's going to go all the way up here, then come down slightly, and over here. So how is this different? You've got NO, right? And these are all gases. What's the enthalpy change over here? What is the difference between the energy of the products and reactants, right? This. So you make a line that's touching the dotted lines and you make sure the arrows are touching. And this is a positive delta H. Okay, so that is the difference between the energy levels of the product and reactant. So this is an endothermic reaction, right? Endothermic. This is exothermic. What's the activation energy? This whole thing is the activation energy. Because it's endothermic reactions need a lot of energy input, right? Whereas exothermic reactions are giving out energy so they can occur at lower temperatures themselves. Endothermic reactions occur at higher temperatures, right? Because they need. So just something to put in. We'll talk about this more in the next chapter. So they are favored or occur at higher temperatures. And these guys are favored at lower temperatures. Why? Because they are giving out energy. So they don't want the surrounding to be hot already. Does
The
this make
class is about
sense?
like yeah.
Haram, question?
No.
Phobia?
I'm fine.
You're fine, right? So I understand I pushed it a bit at the end, but I tried to be clear in my explanation. Read the text, chapter 6, go over it thoroughly. If there's anything that you don't understand, obviously ask me the next
Ask you.
time. Ask me the next time and I'll go over it again.
Okay.
Okay?
Okay.
Okay.
So that's all. And we've covered the entire chapter. So that's great. And have a good weekend.
Thank you. You too.
Thank you.
Allah Hafiz.
Allah Hafiz.